Good evening, everyone. Welcome back to live sessions, NPTEL live sessions for the course Advanced Transition Metal Organometallic Chemistry. So today we will start with the week 4 assignment questions. But before that, we will continue to revise whatever the basics that has been covered from lecture 16 to 20th in week 4. So in the last week live session, we ended up having the metallocene and carbonyl combination complexes. So we were discussing about that. So we will just look about it because this is in continuation in lecture 16 also. So last time what we saw is the reactivity or the preparation of cyclopentadienyl metal carbonyl complexes. So this is what we call a uh, heteroleptic systems where it is not a homoleptic because all the ligands are not same. There are different. One is CP, one is carbonyl. So as you are starting, how we can have a combination of both the things. When we are taking a metallocene is nothing but your metal with two CP rings. Here we have taken a manganese cyclopentadienyl complex with carbonyl when we are reacting under higher temperatures and pressures. So 3 moles of carbon monoxide are being reacted with are being made to react with manganese dicyclopentadienyl complexes under the pressure of 200 bars of CO with 15 hours of stirring and reaction to 90 to 150 degrees Celsius. This much temperature and pressures are required to make this kind of complex where at one side we have a CP ring and the other side we are having carbonyl. So if we calculate the total valence count electron over here, CP will give you 5 electrons, manganese is 7 electrons, each carbonyl will give you 2 electrons. So therefore multiplied by 3, we have 3 over here. So 7 plus 5 plus 6, which is nothing but an 18 valence electron complex. So this is making a stable 18 electron valence complex, whereas if we count here, manganese CP2, manganese was 7 and 2 CP rings will give you 10, that was a 17 electrons. So the reaction is feasible as it is going from 17 electron to 18 electron valence electron thing. So this is way how we can prepare our complexes having both CP and carbonyl ring. Moving ahead, this is another example where earlier what we tried is with your metallocene and the carbon monoxide alone. But now we are taking a combination of metallocene with metal carbonyl. So here it has been taken, nickelocene has been taken, where nickel is in will give you 8 electrons, 2 CP rings will give you 10, and therefore it becomes an 18 electron species. And here it is a nickel 0 carbonyl 4 because carbon is having 0 charge, therefore nickel is existing in 0 state. And it is giving the combination of both CP and carbon monoxide, but it is a dimer now with the release of two carbon monoxide molecules. So both ways we can have a combination of CP and carbonyl attached to a transition metal. Either we can directly react a metallocene with a carbon monoxide under certain temperature and pressure conditions, or we can have a reaction of metallocene with a metal carbonyl to give you, which does not require this much temperatures and pressures, like minimal reaction conditions would be enough to have this timer kind of thing. Moving ahead, what kind of structure is this where we have CP as well as the carbon monoxide? So these are called half sandwich structures. We have discussed in week 1 also, in week 2 somewhere we have seen these kind of structures where one side there is a CP ring, but the other side there is some other ligand. And normally when we have a carbonyl, what we call it as half sandwich, because if there would be two CP rings on both the sides, that is known as sandwich complex. For example, if in case of manganese, this would be both the sides staggered form I have made. You can make an eclipse form also. So that would be a complete sandwich complex. Whereas where we have replaced one of these sides have been replaced by the carbonyl, then that is called as half sandwich complex. So the monomeric CpMCO whole N. So N is not being defined. Depending on the metal and the total valence electron, the number of carbonyl getting attached to the transition metal would be different. They are being called as Haas sandwich complexes. And like for example, here CpMnCO3 is called as cimentrene owing to its diverse chemistry. So it is having its diverse chemistry. That's why it is being given a certain name. Now, when we have seen last time what is the reactivity, earlier we saw the preparation. Now we are talking about the reactivity, how these complexes where we have Cp as well as carbonyl, because initially when we are just having the carbon cyclopentadiene rings with the transition metal, it will give you the same kind of reactions, the aromatic electrophilic substitution reactions, the way benzene or any other aromatic ring would give you because of the high negative charge density on the CP rings. But now we have a carbonyl over here, so the reactive would be different. So here it is being treated with sodium amalgam, and it will give you Na2CpB CO 3 with the loss of carbon monoxide, which we have seen last time also. And similarly, if a dimer of iron having both Cp and carbonyl, when it is made to react with sodium amalgam, it will give you a monomer, which is now then being reacted with a Rx, where R is in positive form and X is negative. And if since it is having the negative charge outside, it will take up the CH3 because of this positive nature, and NaI would come out. So this becomes the reactivity, how we can now attack on the electrophile with the negative charge on the complex because of the presence of carbonyl group inside the complex. Now we are coming and continuing with the cyclopentadienyl carbonyl complexes and their reactivity in lecture 16 also, which is a part of week 4. And looking at the basics of it, we will be able to solve the assignment questions very easily. So it is continuing with the cyclopentadienyl carbonyl complexes reactivity. For example, if we are talking about the reactivity, so earlier we were just looking at the sodium amalgam and that kind of reactivity. Now, how in presence of the halogens, dihalogens, it is showing the reactivity. So if we need to halogenate it, if we want to put the halogen group over there, as we were having earlier, that NeI or something like that, it will also, the dimer will convert to a monomer with a halide group in with it. And in presence of a Lewis acid, this is ALX3, it would be Lewis acid. Any AlCl3, LBr3 you will take. So it would be a Lewis acid. In presence of that, a positive charge will come onto the cation because it will take up the X out, and carbon monoxide is being now it is inside the complex. So one CO is coming here, from 2 to 3 it is going, and one X has been taken by the ALX3 because of its Lewis acidic nature. So this will tend to have a charged or cationic complexes. So for making it a halogenated thing, CCl4 or PCH2Cl, which is a benzyl chloride, that is also a good halogen source under the photochemical conditions. So they can act as a halogen source also besides this H2. If we are using these things, that will also give you a halogenated version. Why we need this halogenated version? Because under certain conditions, and it will give you a charge species which would further react to make required complexes. So now the next thing is ki cyclopentadienyl metal carbonyl complexes, their reactivity, how is their reactivity? Their reactivity is more or less like the same, which will give you the electrophilic ring substitution. So every substitution will happen on that ring itself. Like in ferrocene, they readily undergo electrophilic ring substitution at the CP ring. As I told you, if we are comparing the benzene or if we are comparing this CP negative ring, this would be more reactive when it is getting attached with the metal, and because of the negative charge over here, there is no charge on the benzene as such, but electron density is there. But since we have a negative charge on CP ring, that makes it more nucleophile, and that opens up the possibility or the increases the rate of that electrophilic substitution on its ring carbons. Similarly, as we have seen in the ferrocene case, these kind of complexes where the metal carbonyl group is also there, they will also give the electrophilic ring substitution on the CP ring. And some of those complexes are CP vanadium CO whole 4 thrice, CO carbonyl whole 4. And we can calculate the total valence electron count over here. The CP will give you 5, Vanadium will give you 5 because it is atomic number is 23, manganese is 25. It is the same group of manganese, so it will also contribute 7. So carbonyl 4 into 2, that will give you 18. And here 7 plus 6, it will also give you 18. And here also 5 plus 7 plus 6, that will also give you 18. So these are some stable 18 valence electron complexes, and it will also undergo, when we are talking about the reactivity, their reactivity is more or less similar to that of ferrocene or the metallocenes, where electrophilic ring substitution occurs, and that is very, very feasible. So some of the examples we can say, we can see uh, how the substitution of carbonyl will take place. So any ligand which can give the equal number of electrons to the metal, for example, if I have a phosphine or if I have a olefin over there, so it would be a 2 electron thing. So one carbonyl will also give you a 2 electron, and an olefin will also give you the 2 electrons. So that can exchange, or that can have a substitution of it. So if we make this Cp manganese CO whole 3, which is an 18 valence electron complex that we see earlier, any ligand which can replace one of but that ligand should be giving it 2 electrons, so that the total valence electron count should remain the same. That should be again an 18 valence electron. Similarly, we have a L2, which is diolefin. That means it is giving 4 electrons. Single olefin, that means it is a 1 double bond, and that is 2 electrons. Diolefin will provide you the 4 electrons, and 2 carbonyl is equals to 1 diolefin. And therefore, it can replace both the COs, and we will get 2 monoxide, carbon monoxide molecules outside, and they have replaced the carbon monoxide. So these reactions, they can be accelerated by thermally or photochemically. What it means to say these reactions can occur, but to enhance the rate of the reaction, to get the time, to get the kinetics to be more faster, if it is happening in 1 hour, but if we want to finish it off in 5 minutes or 10 minutes, then in the presence of the light or the thermal activation is required to minimize that activation barrier, and therefore these reactions can be said to be accelerated by thermally or photochemically. So now we are moving towards another reactivity, taking up this rhenium complex where it is bound to Cp and 3 carbonyl. And why we are looking at the valence electron again and again, so you should maintain. So similarly, we have this 5 from Cp. This is called Cp star, where Cp ring has been substituted with methyl at all the carbon positions. This will also give you the 5 electrons. Moving ahead, rhenium will give you 7 because it belongs to manganese group. 3 carbonyl will give you 6, which is the 18 valence electron. Now, in presence of H2O2, which is very known oxidizing agent, and this oxidizing agent will actually give the oxygen to rhenium, and with the loss of carbon monoxide, and therefore it will lead to have this rhenium double bonded O, where it is in +7 oxidation state. Since it is having enough source of oxygen, when we are adding a PPH3, which is likely to get oxidized very easily, so it will take up that oxygen from it, and therefore the molecule get dimerized, and this will give you a dimer like this. Now also, if you calculate, it will tend to give you the same number of electrons as it was giving earlier. So yeah, therefore it has been called as oxidative decarbonylation, because the oxidation is also happening. Here it was in +1 oxidation state, where it has gone to +7 oxidation state here. So this kind of complexes where with Cp, the cyclopentadienyl ring, the metal is having the maximum oxidation state is very rare in nature. Only these kind of complexes are reported where it is existing in +7 oxidation state with Cp ring. And this is the side product. This is very important reaction of oxidative decarbonylation. Now moving, and also if we react it back with the carbon monoxide under certain temperatures and 15 bars of carbon monoxide, certain pressure of the carbon monoxide is required to get back to this carbonyl position, because it is in +1, and that will go to a +1 state easily. Now moving towards, we have another So this was the topic regarding the cyclopentadienyl with the carbonyl. When we were talking about the heteroleptic things, that means the ligands could be other than that of the CP. Now we have another complex where carbonyl has been replaced with the nitrosyl. NO is also one of such ligand which can form a which can form a complex with transition metal, and that will also call as a half sandwich. The geometry, or more or less, it remains the same as that of the carbonyl because it is just replacing or substituting. So nitrosyl, the bit introduction about it, it's a very versatile ligand which can function in two ways. It can coordinate as NO positive, isoelectronic with carbonyl, that means a two electron species, or it can be coordinated as NO negative, which is isoelectronic with oxygen. So here, if you see, nitrogen is bonded with already oxygen, which is having a positive charge. So this is making a three bonds, and therefore this becomes a negative position. The metal becomes a negative as it is giving the electrons to it, as it is taking the electrons from it. Whereas here, when one nitrogen is here and lone pair is here, one electron is here and lone pair is here, the metal tends to give one electron to it. So therefore it becomes positive in nature. And therefore it is called as one electron ligand, and this is called as three electron ligands because it is in combination with the lone pair as well as the single bond also. So these are the two possibilities where it can coordinate as a bent structure as well as it can coordinate as a linear structure. So depending upon that, if it is linearly coordinating with your metal, it would be called as a three electron ligand. Whereas when it is coordinating in a bent fashion, when it is giving a one electron, then it is called as a bent structure. But in both the cases, when it is when we are calculating its oxidation state, or when we are using the oxidation state method, both would be giving in a two electrons. So here we are just considering the neutral methods, how many electrons are being donated by the nitrosyl when it is in either linear or bent position. Some more points that linear structure MNO to bent structure MNO conversion in nitrosyl complexes is triggered by intramolecular transfer of two electrons from the metal to ligand. So as you have seen in linear, it's a three electron thing, and in bent, it is one electron. So if in one electron, when we are giving the electrons from metal to ligand, the two electrons transfer occurs between that from the metal to ligand, then it becomes from linear to bend conversion that happens very easily, upon which a vacant coordination site is generated and associative substitution is possible. So because of this transfer, which can actually occur if we have that intramolecular two electron transfer is occurring, then it will create a coordination site, and therefore our associative substitution will definitely occur where one ligand can come because the site is vacant now. Now any ligand with that much of electrons, they can come and bind with the metal, and that will call as a associative. We have two kinds of substitutions. One is dissociative where the ligand goes and the other ligand comes. Both are substitution, but either if we have a metal in, for example, if I'll say, if it is in 5 coordination, so the coordination number is 5. And if it is losing this ligand, all are L, and if it is losing it one ligand, it is creating a vacant site. And now the another ligand will come and attack over here. That is called a dissociative substitution reaction, where one ligand is dissociating and another is coming into picture. Whereas if we have a metal, and here is a all RLL, and there is one vacant site already. There is a one vacant site. So firstly, it will have the attack of this new ligand with one minus. It will increase the coordination number. The coordination number is now increased from 5 to 6. So when the coordination number is increased, then further after certain conditions, one ligand will go off and this will give you the coordination number back. That is called an associative substitution reactions. That is why it is here being called that when this conversion from linear to bent occurs, there is an involvement of two electrons from metal to ligand. And when the electrons are going from metal to ligand, so there would be a coordination site which is vacant with the metal, and now it can easily take up any ligand from outside, and therefore it will call as a associative substitution. Now moving towards again some for certain points of the cyclopentadienyl metal nitrosyl complexes. So here when we are talking about the general formula, now again becomes this could be N, since we don't know the oxidation state or the charge, and also we don't know the N number is dependent on what would be the total valence electron count on the metal. So depending upon different metals, it would be different. So that nitrosyl ligand in general is a 3-electron donor if we are considering actually as a linear thing. So isoelectronic complexes is possible by substituting 3 CO ligands with the 2 NO ligands. 3 CO, 1 CO if you consider that. Since why are we talking about the three? So here we need to understand one thing. So this carbonyl group is also more or less this carbonyl where it forms a dative bond or something. So this is also a 2-electron thing, and it's in linear fashion. It's in linear fashion. Similarly, when we were talking about this NO, this is a 3-electron donor. It is also linear. So the shape is more or less, the geometry is more or less the similar. That's why we say if we have 3 carbon monoxide group, the 3 carbonyl group, this will be 3 into 2, which is 6 electrons. That can be easily replaced by 2 NO, which are linear. That means 2 into 3, 6 electrons. So the electron count would be same, and that's why the 3 CO could be replaced by 2 NO very easily. So here it is saying that isoelectronic complexes is possible. Isoelectronic means the number of total electron count is same. For example, if it is 18, then it should be 18 in the end in the product also. By substituting 3 carbonyl ligands with 2 NO ligands, or in other way, 1 CO for 1 NO ligand, along with the introduction of a positive charge. So if we have 1 CO is being replaced by 1 NO, that means for 2 electrons, earlier it was 2 electron with the metal, now 3 electron species coming, but now we need to have an isoelectronic that it will give you the positive charge. For example, so if we have metal, if we'll take the same case, MCP, CO whole 3. If you will calculate 5 plus 7 plus 3 into 2, that is 12 plus 6, that is 18 total valence electron. Now, if I am just giving one nitrosyl, so one carbonyl is 2 electron, one nitrosyl which is linear, it is 3 electron. If it is coming here, then it is removing one CO, Cp, Mn, CO whole 2, NO, and lastly, there would be a positive charge over there. So now if you'll calculate the total electrons, Cp will give you 5 electrons, manganese is 7, 2 carbonyl will give you 4 electrons, 1 NO is 3. Outside it is positive, that means we have to subtract 1 electron. Again, it will give you 4 plus 2, 6 plus 5 is 11 plus 7, 18. So therefore, these two species are isoelectronic because the total valence electron is constant. Only the thing is, when we are replacing one CO with one NO, the positive charge will come into picture. Or the other case would be that if we have this Cp, Mn, CO whole 3, if we want to have a neutral complex, so 3 CO would be substituted by 2 NO. If we are giving 2 NO, all the 3 COs will be gone. So it will form 2MnNO whole twice with no charge. Now if we'll calculate again, this is 5 plus 7 plus 3 into 2, that is 18. This is also 5 plus 7, 3 into 2, that is 8. Or we can call it as 2 into 3. So this is also called as isoelectronics. So based on that, nitrosyl and carbonyl can have this substitution and replacement, because one nitrosyl and one carbonyl can be exchanged with the number of electrons, or they are donating, or they're making a bond with metal. So therefore, one CO for one NO ligand, that will introduce a positive charge on the complex, that means on the metal. Now, in the next lecture, in 17th lecture and further, we saw how these complexes are look like, how they look like. For example, we have certain cyclopentadienyl metal nitrosyl complexes where it is having combination of carbon monoxide also and simple nitrosyl complexes also. So these are certain examples. Now we come to the preparation of how these cyclopentadienyl metal nitrosyl complexes. So earlier what we saw, to make a carbonyl, metal carbonyl with CP ring, either we can have a metallocene with carbonyl directly, carbon monoxide directly under high pressure and high temperature, or the second way was to have a metallocene with a metal carbonyl, if we are taking, or any X form of that matter, that will give you the cyclopentadienyl metal carbonyl thing. So these were the two main preparations. Similarly, the first preparation is we are taking a metallocene, and instead of now carbonyl, we have a nitrosyl. So this is also a general thing, metallocene plus a nitrosyl, and therefore we end up having a CP with N. So here we can see that it is having this is a 20 electron thing, valence electron, but this is now 18 valence electron. So one of the C5H5 ring will go out and as a dimer, but the half molecule is saying that half C10H10 is nothing but C5H5. Similarly, when we have cobalt, which is in C5H5, two molecules of this metallocene. Now, firstly, we saw, so here we can write it like this way. We can compare with the, so for the preparation of preparation cyclopentadienyl metal nitrosyl. So for the CPMCO, I'm just generally taking it, this particular thing, either we were having the metallocene plus carbon monoxide directly. One method would be this, or metallocene with metal carbonyl. We don't know how many carbonyls are attached with that metal. So these were the two preparation methods. Similarly, if we have metal nitrosyl, we want to make this particular thing. Now, again, we will take the, instead of this metallocene plus nitrosyl, this is first preparation, or we have CPMCO whole N, and now we are replacing the replacement or the substitution of the carbonyl via nitrosyl. So this was the second method as it is shown over here. When we have CP carbonyl, two NO are there. Now two NOs, both the four NOs, because two molecules are there, both the four has been replaced with two NO, and that has given you a dimer. So 4 CO would be 8 electron, and since it is coming as a dimer, so it will also compensate the total number of electrons. So this is one more method. Another method, when we have NO positive HSO4 negative, and here we ended up having both carbonyl as well as a nitrogen. So it's a combination of both carbonyl as well as nitrogen. So these are certain preparation methods which are more or less similar to that of what we have seen to while we were preparing the cyclopentadienyl metal carbonyl complexes. Now, talking about its structure again. So NO can be terminal as well as bridging ligand, as we have seen in carbonyl. So here we need to understand like carbonyl can occur as terminal as well as the bridging. It can bridge with one metal or two metals or three metals, depending on how metals and like three metals they can have a bridging with that. So it could be new one fashion or new two fashion or so on and so forth. Similarly, nitrosyl will also play the same way. Special features is the MNO bond angle. So we need to see what kind of bond angle, whether it is in linear or it is in bent, whether the bond angle is less than 180 or more than 180, or exactly equal to the 180. Linear structure MNO and bent structure MNO complexes are possible. So we have these kind of things. Now we will see one of such examples where the properties are being defined, how the bond parameters change when we have different kind of coordination like bent on linear or bridging terminal. So these four things are there in the metal complexes. So this is a dimer where one side it is CP ring and others are the NO. So this is again a half sandwich complex. So here, if you will see, this NO is in linear. This is terminal, but linear. This is also terminal and linear. And therefore, the bond angle, as you can see, between N and O is around 160 degree, which is closer to 180. That means a linear. And the bond parameter is, the bond length is 118 picometer, where chromium and nitrogen bond parameter is, bond length is 169 picometer. Similarly, if we have this kind of picture where now both the NOs are in linear fashion, so they would be having the similar properties. When we are having a bridging thing, now see the NO bond length is 119, which is more than that of the linear one, the terminal one. And also the chromium nitrogen distance has been increased from 169 to 196. So what we are looking at, this bridging is having, or the linear one, the terminal one is having more bond strength. So both in case of be it NO or be it metal N. So both this case, this is less. When the bond length is less, the bond is stronger. That means the frequency would be more. As you can see, if we compare nitrosyl linear, it is 1677, whereas it is in bridge, it is 1518. So this is having more strength. More frequency means more strength. So that's why its bond length is less compared to the other one. So frequency is inversely proportional to the length. Free nitrosyl would definitely be 1876. So that is more important. Then frequency of NO positive free, which is having a positive charge. Now the frequency even becomes more. So that is 2250. So this is where we have to define how the things are working. If we see nitrosyl as a linear and the terminal position, the frequency of NO would be around 6,000, 16,000, 1,600 or something, whereas the bridging one would be having less frequency because the stretching frequency we are talking about here, because the bond wavelength or the length is inversely proportional to the bond frequency, as it is tightly bound or strongly bound in the linear fashion when it is coordinated in a terminal way rather than the bridging, because now the nitrogen is coordinating to the two metals. So the frequency has become, or the bond strength has become little less compared to when it is coordinating only with the metal, one single metal. So this has been given by Fontana in 1974. Moving ahead, another property, another molecule where it is having nitrosyl. Earlier we saw NO ligand, which is in linear. So I'll just. So earlier we saw the NO, which is terminal but linear, bridging. There also it was linear. So the bond angle it was around 176 or 179. So it was linear only. Now the second case is a comparison of a bent, as you can see. Now the metal NO, the bond angle is 138, whereas metal NO, the bond angle is 178. So now this is bent one and this is linear one. Here now we are comparing the bent and the linear one. So as you can see, the linear again is more frequency compared to when we have a bent one. Bent one is less tightly bound because of, as you can see, the bond length is very high, 185 picometer between metal and nitrogen and 117 between nitrogen and oxygen, whereas metal and nitrogen of the linear one is 174, which is less than that of the 185. So therefore, the strength is now more in case of the linear compared to the bent one. That's why the frequency, the NO stretching frequency in linear case is 1845, and in this particular structure. So these can have a variation when we are comparing the two things. Earlier, we were comparing the terminal as well as the bent one. So the values were different. Here we are comparing the linear and the bent one. That means there was a terminal and bridging comparison. Here it is a term a linear and bent. Both are terminal only. So both are terminal one. So again, the terminal linear is having more frequency compared to the bent one, and the free and the nitrosyl with the positive charge, they remains almost the same because they are not coordinating in with the metal. That's why they are free in nature. So this is where we are reaching. And the another complex is nickel nitrosyl, where it is only having one nitrosyl group and with the 180 degree. But during the oxidation calculation, when we need to calculate the metal oxidation, we have to consider the charge on the nitrosyl as positive. Therefore, it will give you the nickel as +2 in nature. And if you will see here, now again, these two values are remaining the same if you'll compare all the three different structures, but the linear is now having 1830 because there is no comparison of the bent, and the frequency of NO bond depends on various factors, how coordination, how it is coordinating with the metal, how much electron density is there with the metal, because it is dependent on the strength. So if it is electronegative or it is electropositive, so depending on that, NO bonding stretching will also be affected, but the trend would remain the same. For example, the trend what we have seen. So we saw if we will compare comparison of terminal NO with bridging NO. So we saw that stretching of NO terminal is greater than stretching of bridging. Easy reason, because the strong bond would be with the one metal rather than coordinating with the two metals. So it will reduce your bridging because now the electron density is now going there also. So the bond gets weakened when we have a bridging mode. Similar case happens when we talk about the carbonyl. So when it is a new carbonyl terminal is having more is strong bond or having more bond strength compared to the carbonyl bridging. So as bridging increases, as it increases, the frequency reduces. Whereas if we compare similar trend, if we compare the linear versus bend, again the linear one, so if we'll say this is decreasing frequency, that means linear is having more frequency compared to bend, more bond angle, more bond frequency, stronger is the bond. So it is around 180 degree, that would be around 138. So that's why it makes a stronger bond compared to the bent one. So this is the general trend. And the values could be here and there, but it will always come in the comparison mode. Okay, if it is having linear or linear or bent, then which one is making the strong bond? Or if it is in terminal, or if it is in bridging, so which one is a stronger bond? So here it is the journal example where we are not looking because we're looking into the bridging and terminal, because there is only one nitrile which is coordinating with your nickel in a linear and terminal fashion. Here the bond angle is 180 and the frequencies is straightforward, where it lies in the region of 1830 free, and having a comparison of the free nitrosyl or the charged nitrosyl would always be having more frequency compared to when it is coordinating to metal, because there it is giving the electron density. It is dependent on many factors, but the free ones are totally devoid of such things. Moving towards next example, where we have the CP rings and NO. This is being called as a fluxional. Why we are calling as a fluxional? Because fluxional means when it can change its hapticity. So by fluxional, change in hapticity or the number of electrons it is. So anyway, you can, or the number of electron it is giving to the metal complex. For example, that eta 5, this CP ring is right now in eta 5, but if you give a certain temperature, it might go from eta 5 to eta 3, that we have seen in a Alai case that it goes from eta 1 to eta 3. So this happens, that is called the fluxional behavior. Similarly, NO linear could go to the bent form, because that could be having a 1 electron to 3 electron transfer. That intramolecular transfer was happening that we read earlier. So this kind of fluxional behavior is possible when we have other ligands which can go from one hapticity to the other hapticity. For example, if we have this linear one, so this is giving you a 3 electron in this. Now if I need to make it as a 1 electron, that means a bent position, then this CP ring, which is right now in eta 1, it has to go in eta 3. So we will explain it a bit more. So here we have structure is manganese over there, molybdenum, sorry. So we have molybdenum, where there is one CP ring. And there is one nitrogen. So this belongs to chromium family. So it would be, if we'll count the electrons, so 5 from 1 CP, molybdenum is giving you 6 electrons. Another CP would be giving, this is 5, this is 6, this is 1 electron, this is 5 again, this is 3 electrons. So 1 plus 5 plus 3. So here it is 11 plus 1, that is 12. 12 plus 8 is 20 valence electron species. Okay, this is 3 electron. So now if, why I'm talking about, so if I have to maintain it, now at room temperature, it will show a fluxional behavior. For example, here, these remain in their eta 5, but this position, this is eta 1 in nature. Now, if I will take where it is giving me 3 electrons. Okay, so one bond would be there or something like that. So now it is eta 3. So this will become now 1 electron, because the 2 electrons are being coordinated here. So this will now become 3 electrons. This will become 1 electron. Earlier this was 1, this was 3. So the fluxional behavior occurs when we have to make an isoelectronic species only, but this could occur at a certain temperature. Sometimes some complexes require more than the room temperature. Sometimes they require a less temperature, but depending upon the metal properties and the complex properties, it could show the fluxional behavior. If you have those kind of ligands in the complex, which can actually show that behavior, they can change their hapticity from one to other. They can go from higher to lower. They can go from lower to higher also. For example, here it goes from eta 1 to eta 3, which is lower to higher, whereas NO, which goes from 3 electrons to 1 electrons. So this kind of behavior is called a fluxional thing. That's why in this molecule, this has been written that fluxional at room temperature. And here the frequencies, here if you'll see the 179 degrees, and now in this particular molybdenum complex, the linear thing, which was earlier in nickel case, it was 1800 something. Now it is 1610 over here. So depending upon the metal and the coordination around it, the electron density and the bond strength that gets affected, and that's why the frequencies are not constant. That's why in case of free one, that is constant, but when it is coordinated to metal, having a certain ligand scaffold around it, and the environment will be changed, and therefore we will be having different parameters. So the lecture 18, which will, I guess, comprise of all the properties, more or less from the 19th and 20th also. So this is, earlier we have come to the point, we have seen the transition metal CPM simply. This is metallocene. We have seen so far one CP and different carbonyl groups, one CP with metal and nitrosyl, or having combination of carbon and nitrosyl both. And here we have the combination now. We need a CPM and this hydride bond. So this lecture is all about the transition metal cyclopentadiene hydride complexes. So mainly these kind of hydride complexes observed in 4D and 5D because of their reactivity. But in case of the 3D metal, they generally tend to dimerize with the loss of the H2. So certain 3D, 4D, 5D, like you can see tungsten and molybdenum, tantalum, they're making the hydride complexes. So this will be stable in case of 4D, 5D, but in 3D that will not be very much stable. They will be very reactive and therefore they tend to lose the hydride. So now the question comes with the preparation method. So here we have taken a salt metal halide where molybdenum chloride has been taken where molybdenum is +5. Now we have taken sodium C5H5, which is a Na positive and C5H5 negative. This is a Cp negative, and this can replace easily with the loss of NaCl. Also, we have a reducing agent that is a NaBH4, which will provide the hydride. So this is actually acting as a hydride source over here. So under this condition, because treating the certain chlorides or metal halides with the sodium borohydride or for any matter C5H5 or this reducing agents, we need to maintain certain temperatures. So this will tend to give you the Cp2 molybdenum H2, which is having a plus for oxidation state. Now, in presence of a reducing agent, as you can see, it has gone from +5 to +4 with the involvement of the H. Hydride is over there. Now, this is more or less stable, air stable. If you'll take the rhenium chloride, similarly, if we have any C5H5, it will take up the H directly from the C5. And therefore, since we are using the two molecules, and this will tend to give you the C5H5 rhenium hydride already. So this has gone from +5 to +3. Na C5H5, this is sodium cyclopentadienyl salt. It itself is a reducing agent, but when we have the sodium borohydride, that requires certain kind of low temperature conditions. So moving ahead, we have certain properties that we need to look into before jumping to any kind of other structures or something. So Cp2 rhenium hydride, that cyclopentadienyl complex with the rhenium having a hydride bond. This is being given by Wilkinson in 1955. This is quite stable, air stable and diamagnetic, of course, when compared to Cp2 rhenium. If you'll count this will give you 10. This is a 7 electron. This is 1 electron. Therefore, it is 18. So 18 valence electron becomes a diamagnetic thing. Whereas this is a 17 valence electron. That's why the other one is the hydride one is air stable and it is diamagnetic. The investigation of this Cp2 rhenium H was one of the first application of proton NMR spectroscopy in organometallic chemistry. As we could see, the hydride 1H of this 10HCP, the Cp that we are having, that was coming around 3.64 ppm, whereas the hydride was coming, metal hydride would mostly it will come in the negative region because of the high electron density. It will go to the upfield. So this is a part of NMR spectroscopy. So this was being seen in at minus 23.5 ppm. So therefore that complex is really, really important. Now moving towards these are the structures. So generally these hydride complexes where CP rings are there and hydride is there, they will tend to form a tilted. As you can see, the CP rings are kind of tilted. So that's why they are being named as like that. Now, certain preparations, how we can form it. One most important reaction of the rhenium where we have a CP and double bonded O and chloride over there. Now we are using a very high reducing agent. It's kind of very strong reducing agent in presence of alcohol. So this will tend to give you rhenium in +7 oxidation state, as we have discussed earlier also, when we give that oxygen source, that H2O2 tends to form that rhenium with double bonded O all the way. And this form with the hydride in +7, it's very, very rare. And this is one of the first complexes where we can define the rhenium hydride bond frequency as 2018 centimeter inverse. So this is having the tendency to accept large number of hydride ligands in the coordination sphere. So as you can see, ReH7, ReH9. So these kind of complexes are quite stable because it is giving a +7 oxidation states and accommodating maximum number of hydride things. So now we have certain characteristics. So the proton NMR spectrum of these hydride ligands show a separate signals for the equatorial and axial protons at -90 degrees, whereas at 60 degrees coalescence occurs because of the rapid exchange of the equatorial and axial positions. So protons. So for making this system to understand what they are trying to say, if we have this, suppose I'm taking a general case where I have a hydride H and this is equatorial. So when this is occurring at a 60 degrees, so the exchange becomes so faster. Exchange at 60 degrees is so fast that we will get an average environment. We could not able to segregate which one is equatorial, which one is proton, because both will come as in which will they will give you the average spectrum. So the exchange is very, very fast. So if you want to clearly see how many axial protons are there, where they are coming compared to the equatorial protons, so they need their movement has to be restricted. Movement or exchange has to be restricted. And for that matter, how we can restrict their movement? By lowering the temperature. So when we lower down the temperature, for example, -90 degrees, which is the high lower temperature. So when we low down the temperature, what happens? Their exchange becomes very slow. So now the NMR spectroscopy, that instrument, their relaxation time and that matches with their exchange time, and then therefore the instrument can detect whether this is axial, that is equatorial, their chemical shift values would be different. But when the exchange is so fine and that is very fast exchanges happening, instrument tends to believe that okay, both are same because the exchange is very fast. So that will not able to capture both of them separately. That will come as an average environment. That's why it is said that at -90 degrees we can segregate or we can get the two separate signals for equatorial as well as the axial protons. Whereas when at room temperature or more than room temperature, this is more than room temperature, so the rapid exchange between these hydrides occur, and therefore we could not able to see which one is axial, which one is equatorial, and both will come at one position. So now coming back to the reactivity, we have seen the preparation, we have talked about its properties. The last factor is what are the reactivity of cyclopentadienyl metal hydride complex. So Lewis basicity of the central metal atom decides the reactivity of CP metal hydride complexes. So depending upon what kind of negative charge is on the metal, so that will lead to certain reactivity. For example, here, this is C5H5 whole twice MH2. So in presence of this H positive, these metal hydrides, CP metal hydrides, they tend to get protonate very easily because of their negative charge. So they will take up the H positive and the positive will come out. Most probably it is a molybdenum and tungsten. Similarly, if we have rhenium, that will take up the H and will give you the positive charge. Similarly, if you want to go back to this particular thing, so OH negative, if will give that one of this rhenium, there are two H. So one of this rhenium will OH will take up this, and again the charge will come back. outside already it was positive, the negative because of the loss of the proton. This will counterbalance and that will give you again a neutral CP metal hydride complex. So this is where we need to be emphasizing that these metal hydride complexes where CP is attached, they're prone to get protonated if you have a very strong acid or something in it's present. So this was all about in the week 4, what are the basic concepts. So far we have seen that, so we have in this particular lecture, we have covered that CpMCO whole N, their preparation we have covered, properties and their reactivity we have covered. Then we saw that how NO can be formed from the CO, their reactivity, properties, and a mixture of CO and nitrogen we have covered. And the last complex that we saw is the metal hydride. Same way, their properties and how the reactivity and how they are having the basicity nature to get proton easily. So this week 4 was all about these different kind of different classes of CP complexes where the substitution has been different. So now we will quickly take up the questions of week 4 assignment and we'll see how we can able to solve this. So here we have the questions for I hope this is visible to all of you. So there would be 4 questions again in week 4 assignment. So the first question we'll take up quickly. The first question says for the following compound, linear and bent NO moiety, that means the frequency in infrared spectrum typically appear respectively at. So we need to find out at what range the linear and bent frequencies that occur in case of the ruthenium. Firstly, we should note that frequency for the NO linear is greater than the bent form. And if you'll see the 4 options, one option is already eliminated because it is asking for respectively. So the linear can't be lesser compared to the other one. So 2000s and 1900 is reached for the free thing. So free nitrosyl or free nitrosonium ion, they come in a region of 2000 mostly. So only left option is 1845 centimeter inverse and 1687, which has been actually proven by the IR. So I'm just telling you how to eliminate the options when you have 4 options and you can see, okay, the first option can't be true because the linear one has to have the greater frequency. And in mostly all different types of cyclopentadienyl metal nitrosyl compounds, we have seen that what could be the possible range. So the maximum range we saw for linear thing was going up to the 1800s. So it never crossed 1900, it never crossed 2000. So that is why we eliminated the B and C options, which is belonging to the free NO or free nitrosonia. And therefore we ended up having 1845 and 1687 for the linear bend. As I've already said, how we are getting to know this is a bend as the bond angle is less than 180 degrees. And this is a linear where the bond angle is quite approaching 180 degrees. 178 is approximately equal to 180 degrees. And since this would be the bond length, so if we'll say the bond length of metal N bend would be greater than metal N nitrogen linear. Similarly, not with a much difference, NO bent bond length would be greater than NO linear. So in both the cases, because of the frequency of the bond stretching frequency, this is nothing but we are talking about the stretching frequency. It is when that is higher. Also, second question we can relate it as the bond stretching frequency is inversely proportional to the bond length. Bond stretching frequency is directly proportional to the bond angle. That is why, if generally also you will see, in case of linear, the bond angle is greater than bend. That is why frequency is greater than bend and length is smaller than bend. So these things that we need to note. And in this particular case, the bent one is having 16,18,7 centimeter inverse. This is NO. We are not talking about the metal nitrogen. This is nitrogen oxygen. And similarly here, it is 1845 centimeter inverse. So hope this is clear. Now we will move to the second question. Second question is also interesting because now this is another property. They have already given one step ahead. This has been made from some different, earlier there was a reaction of the rhenium chloride or something in presence of H2O2, which will give you the rhenium in +7 oxidation state. So this will give -2, -2, -2, and -1. So this will give you a oxidation state of +7. Now, since we have enough oxygen source in the rhenium complex, so PPH3 is that compound which tends to go from its +3 oxidation state to +5 by making a P double bond O PPH3. So that is why it will tend to give you this particular dimer where with the loss of P double bond O. So if we have two molecules of this, it will lose this PO PPH3 and we will tend to have this dimerized where it is bound linearly also, it is bound in a bridging fashion also. So this will be having a complete reaction of this will be having a complete reaction rhenium CP star I'm writing where CP star is nothing but your cyclopentadienyl ring with the substitution of methyl. So everywhere it is methyl. So when we have double bonded O, so here there is PPH3. It will release the PPH3 with rhenium making double bonded O over here and CP star here, CP star here. So with the loss of P double bond O, PH3. Okay, so both they have asked for the product. So these both are the products. We can't ignore this method. So C and D are the options for that. Moving ahead, we have third question. For the following compound, the NO moiety. Again, you need to see the in the bracket in the centimeter inverse. That means they are asking for the stretching frequency. In infrared spectrum typically appears. Now, this is a complex where only one NO is there, no bent, no linear, and this will give you a range of 1610. So here, molybdenum NO, this is linear, having bond angle of 179. So frequency of NO is 1610. So depending upon what kind of ligands are also there and electron density, the bond stretching that gets affected. That is why in case of this compound where complex where we don't have any other linear or bent or bridging terminal, we are not talking about that. There are two CP rings, three CP rings actually, where two are in eta 5 fashion, one is eta 1 fashion. So this, because of the electron density of the molybdenum, the bond stretching has been affected on the NO bond, and therefore the answer is 1610. So this was the only complex which is fluxional at room temperature that we have discussed. At room temperature, either when that fluxional means that if NO linear goes to NO bend, that means if the contribution goes from 3 electron to 1 electron, so one of the CP rings which is this is coordinating to metal, this is 1 electron, now this will go to metal. So this will go to 3. So this is called the fluxional behavior that occurs at. So for the isoelectronic species, the fluxionality is happening at room temperature. Okay. Taking up the fourth question, we need to find out the correct statements about this following metal complex. This complex we have taken. Now it is asking for the statement or statements is an R. So we cannot just tick or see one single statement. We need to see all the 4 options. So firstly, the oxidation state of the metal is in +4. As I told earlier, to calculate the oxidation state, normally we consider the oxidation state of NO as it will give you the +1 charge on the metal because it becomes a -1. So therefore, from 3 CPs, it will have -1, -1, -1, X is -1. Therefore, X become a +4, which is nothing but your oxidation state of your. So this statement is right. The metal complex is fluxional at room temperature. We have already seen because there are ligands which can change their hapticity from -1 to -3 or electron density from 3 to 1. So therefore, it is at room temperature. This is not a piano stool geometry. So the C statement is wrong. And also we have seen in the earlier question that the stretching frequency of NO is 1610. So all the 3 points are correct except the C point. Now moving towards the oxidation state of the metal in the following compound, as I have told that it will impart a positive charge on the metal. Therefore, -1 coming from Cp and -1 coming from NO, this will give you an oxidation state of +2. So the C option is right. The C option is right, where the +2 nickel is existing in +2 oxidation state. Okay. So that were quite straightforward questions that you can know. And now the sixth question says, we have a rhenium complex with a CP and double bonded O and Cl cells. Here rhenium is in -2, -1, -1, -1. So it is in, rhenium is in +5 oxidation state. So when we have these kind of reducing agents where it can accommodate many hydrides, so it tends to form this rhenium HHNH species without any doubt, where rhenium exists as +7 oxidation state. So here it gets stabilized in presence of this, which we have seen earlier also in the presentation which I was showing you. So here also, this is a kind of exception, or we can say that in presence of oxidation state, it is going from this +5 to +7, but actually it is accommodating more hydride things. So that's why this is having a kind of accepting nature of having hydride in its scaffold and giving an oxidation state of +7. That's why it's a very straightforward reaction in presence of lithium aluminum hydride, which is a hydride source over here. In presence of methanol, it is giving you a rhenium complex in +7 oxidation state where 6 hydrides are there. Now, in the seventh question, it has been asked the following compound is known as. So we just need to name the thing. So if we calculate the oxidation state, it will come as +4 because Cp will give you -1. This is -1, -1, -1, and therefore it becomes zirconium as +4 oxidation state. If we will calculate the number of valence electrons, Cp will give you 1, 5. Zirconium belongs to titanium group, that will give you 4. Another 5 from Cp, 1 from chloride and 1 from hydride. So this will give you a 16 electrons, valence electron species. So this is nothing but a Schwarz reagent. So this is the name of this particular complex, which is very, very important complex. So now moving towards another interesting reaction, which is the product of the following reaction is, so we have the product of the, we need to find out the product of the reaction as we have already discussed. In case of 4D, 5D, 4D and 5D metals, they will form the hydride complexes. But in case of 3D metals, the hydride complexes become so reactive that they get dimerized on the loss of H2. So this was a general statement, but here the scenario is we are using a hydride source, or we can call it as a reducing agent. So it is here to make a hydride complex with titanium. As you can see, because of this titanium, it is losing the H2 with the loss of BH3. 1 by 2 B2H6 is nothing but your, if 2 into cancel, this is the loss of BH3. Only one BH4 because we are using two NaBH4, so only one BH4 is left and two NaCl. So both the Cl has been taken up by the Cl. So what it would form? It can't form this hydride because it is not stable. So this will cancel out. But also we have BH4. Agree that it can make a dimer also, but because of two equivalents of NaBH4, it will lead to have this kind of eta2 bonding from the BH4, which coordinates with the titanium and reduces its oxidation state. So therefore, if in any other case, we can't have the Cl over here because sodium will definitely take up. Already in the reaction scheme, it is shown that sodium has taken up the Cl. So we can't have any Cl. So this also gets only the confusion between B and D, whether it will form this kind of species or we will be having this kind of species. So H2 has been lost, only the H will come from the BH4, which is coordinating as a eta2 fashion. Now the ninth question is, it says that for the product, now, as you can see, this was the answer in the earlier case also. So we are taking the titanium chloride with the Cp2Mg. So when this kind of case is happening, this is a reaction where we are employing the Cp rings. So this is to make a metallocene kind of thing, but not exactly metallocene because we will be ending up having other ligands also. So this is the preparation method. So since we have Cp2Mg, definitely that Mg will take up the chloride. As you can see, it's a 2:2. So we have 6 chlorides over here. 2 into 3, 6 over there. And if we have, so 2 will be taken up by MgCl2 will be gone out. So since 2 Mg are there, 4 Cl will be gone out, only 2 are left. So to balance that thing, we will be having Cl and Cl in the picture. And the other Cl will be replaced by the Cp rings that we have. Now, which one is the possibility? This couldn't be the possibility because the Cl is going, the Cp has to be adjusted. This can't be the possibility. Among these titanium and titanium, again, we can calculate the number of electrons or something like that. If Cp is 5 and other Cp is 5, one chlorine, if it is 1 electron, other will be like 2 electrons. So this would be whole and with 4 of titanium. So this will give you a 17 electron and 1 electron here you have with the titanium. So this will 18 valence electron thing. So if it does not have a direct bond with that titanium and titanium, that won't be forming any 18 valence electron. For example, here, if we are calculating the titanium chloride as 1 electron, this will be giving a 2 electrons to here. And this is 5 and 5 plus 4. 14 plus 3, 17. So that's why we need a direct metal to metal bond to complete its metal total valence electrons. That is 18. That is why the C option is correct and not the B option. So you need to be very careful when you are looking around whether you can cross calculate if you know the structure, or if you know the total valence electron, it should be like this way, and you can find out the number of metal-metal bonds also. So the last question of the week 4 assignment is we need to find out the product of the following reaction is. So as we were looking at this kind of complex, zirconium having a positive charge, which has come from the short region itself. So then, since this is a positive charge, so alkene being an electron rich thing, it will coordinate with the zirconium, and then the CH3 will back attack on your thing. For example, here, if we'll just show like this will go and connect with this particular form, and therefore this is called an insertion reactions, where the alkene is getting inserted between metal, that is zirconium, and CH3, that is argon. So maintaining the charge, because it is nothing related to the charge, it is not, this is a neutral ligand, therefore the charge remains the same. So this can't be the option. A is the option. So here we have finished up the questions for the week 4. So these were the kind of straightforward questions from the lectures that has been we have discussed so far in the first half of this live session. So again, if you'll go through one more time through what are the concepts that we have seen. So I will just give you a brief of it. So the main features that we saw here in or so the important features that we saw was to see whether, okay, the bond stretching frequencies is nothing like fixed for, we don't say that stretching frequency for NO linear or bent terminal or bridging, it is fixed. They're not fixed. They can be modified or they can be modulated depending upon the ligand scaffold, also the metal electron density, and so on and so forth. That's why in one case, if metal, sorry, not NO linear, it is 1800 or something approximately. In other case, it would be NO linear 1600 also. So depending upon the metal, you need to see whether the electron density is there, because bond strength will depend upon many factors. The how the electron density is working, what is the oxidation state behind it, around the metal, and also what kind of substitutions are there with the metal, whether it is electron rich or electron deficient. So depending on that happens. Another factor that we saw, okay, so another factor that we saw, also the second factor was we need to remember that stretching frequencies for NO linear is greater than bend. Stretching frequencies of NO terminal is greater than bridging, because it is now coordinated to more than one metal center, so therefore the bond gets weaker. The bond length is inversely proportional to frequency. Therefore, bond length in case of NO terminal is less than NO bridging. Not much difference, but still NO linear, then bent. Also bond length of metal N, terminal or linear, is less than metal N from bridging or bend. So this we need to remember. So then we see that how the preparation of metal carbonyl and metal nitrosyl takes into picture, and we need to assign the different properties, the fluxional behavior. So if that was an important concept where we have a metal with Cp in eta 5, Cp in eta 5, normally the molybdenum, Cp in eta 1, and NO is 3 electron, that means linear. So it will show the fluxional behavior at room temperature. So this eta 1 can go to eta 3 and 3 electron NO can go to 1 electron NO, that is linear to bent. So most importantly, these three main features that has been highlighted. And besides that, there were reactivity questions that we have covered so far. For example, here, the alkene insertion that we have seen, how the metal CR, this is nothing but your metal R and alkene is coming and getting inserted to it. So this is the metal insertion reaction, alkene insertion reaction. Here we saw how the CP rings are getting attached to metal, but here also you need to find out what kind of whether metal-metal direct bond is there or not. Again, we can calculate by considering the total valence electron as 36 around total because of two titanium centers. So now if we'll consider this is Cp whole 4 titanium 2 Cl2. So Cp whole 4 it's 5 into 4 plus titanium is 4 plus into 2, 2 into 2. Or if it is bridging, we will consider 3 electrons. So bridging, already I've shown, bridging Cl is 3 electron, whereas terminal is 1. This is total 36. X is the number of electrons for making a bond. So 20 plus 8 plus 6 plus x equals to 36. This is 34, x 36. So we get x equals to 36 minus 34, which is 2. So therefore, x equals to 2 electrons to make one bond. So titanium and titanium bond. So metal, metal. So from one single question, you can answer so many, one single concept, you can answer so many questions. So one metal, metal bond is there. So if you know this, then you can just see the answer and then you can mark it. For that matter, you need to understand or know what kind of total valence electrons are there. Similarly, here we saw how the 3D metals, they will not give you the direct hydride complexes. They will get dimerized or with the loss of the H2. But what kind of dimer is going to exist or how it is going to form, because all the H has been taken away, only the BH4 is left, which will be coordinating with your metal in eta 2 fashion. So this is a eta 2 fashion where two H are binding to your titanium. Also, we saw something where we just need to name this particular compound. So this is a short staging. Here we saw in presence of a hydride source and methanol, it is giving a hydride complex where rhenium is in +7 oxidation state. So it's one of the rare complexes which can accommodate a maximum number of hydrates in its capacity. So here we need to find out the oxidation state. While generally taking oxidation state into consideration, we take the NO as minus. So therefore it will give a plus charge to the metal. Here also we need to find out which other statements are correct. So this was the main molecule, important molecule where it shows the fluxional behavior as we have the CP rings and the nitrosyl. And here also we saw the fluxionality and how the stretching frequency is now 1610 feet linear in linear form, whereas in the earlier case, we here also we saw that if it is having a mini oxygen sources, so PPH3 will take up the oxygen very easily and goes from plus 3 to plus 5 oxidation state, giving a product of PPH3PO, PH3PO, and a main product of this dimer of rhenium. And here we have seen the first complex where the bent and linear are given and we need to define or assign the stretching frequencies. So this was all about the week 4 assignment questions and the basics covered from lecture 16 to 20th. If you guys have any doubt, you can just ask me regarding the questions or any query regarding the lectures. We will wait for 10 more minutes. If you guys have any question, then we will clear. Otherwise, we can have the question session next Tuesday from 6 to 8. Since we don't have any questions right now, so I'll end up the live session now. Hope to see you guys soon in next live session from 6 to 8 on Tuesday. Thank you very much.